So this is an explanation of the alternate problem 1 for exam 1, where we have omega 1 rotating the link OB about the x-axis and omega 2 rotating the link BC about the z prime axis. The first thing it asks us to do is find the angular velocity of BC. So that's just kind of from observation of the diagram. You can see omega 1 is about the x-axis, so that gives us the omega 1 I term, and omega 2 is about the z prime axis, and it asks for all the answers in terms of the inertial frame. So the rotation matrix for a z-axis rotation is shown here, and the k prime is just equal to the k. So the angular velocity of omega BC is omega 1 I hat plus omega 2 k hat. And for the angular acceleration, omega 2 is constant in this case, so the derivative of that is 0. So all we have to focus on is the omega 1 term. So we'll have the ordinary derivative, omega 1 dot I, plus our transport theorem term, omega 2k cross omega 1I, and then using the right-hand rule, that's going to be in the positive j direction. So the angular acceleration is omega 1 dot I plus omega 1 omega 2 j. And then the third part asks for the velocity. So the first part of the velocity is determining the position. And again, that's done from inspection of the diagram. The RB is just this length 1 along the x-axis in the I direction. And then R from B to C, or R of C relative to B, is the length 2 times the cosine of I plus the sine of J. And then the velocity of C is R dot B plus R dot C relative to B plus omega BC cross R C relative to B. And both of the R dot terms are 0, so they go away. And we just have this cross product to take care of. The omega BC we get from the first part of the problem, and the RCB is from the position that we determined just a second ago. And so the I cross I is 0. The I cross J is going to give us our first term, which will be in the negative I direction, negative omega 2 L2 sine of theta I. And then we have omega 2k cross L2 sine of theta j, gives us a positive omega 2 L2 cosine of theta j. And omega 2k cross the L2 sine of theta j gives us I have a typo there. I think that might need to be an omega 2. No, k cross. Oh, no, sorry. I'm getting confused looking at the camera and the paper. Negative omega 2 L2 sine of theta j, and just rearranging our terms. Here's our final answer. For the acceleration, we have the angular acceleration cross the position of C relative to B, plus the angular velocity cross the position of C relative to B. And so I broke this up into the first cross product and the second. The first cross product, we just take our angular acceleration from the second part of the problem, crossing it with the position from the third part of the problem. And again, that's just doing the right-hand rule a bunch. So the omega 1, the I cross I is 0. Omega 1, omega 2, or then omega 1I cross L2 sine of theta j gives us omega 1 dot L2 sine of theta k. Then we have omega 1, omega 2 j cross L2 cosine of theta I That gives us negative omega 1, omega 2, L2 cosine of theta k, and the j cross j terms are going to be 0. Then we have the omega bc cross r of c relative to b, and this is our velocity from the previous problem, and this is the angular velocity from the first part of the problem. So we just get those parts from the previous parts, plug them in, and compute the cross product. The cross product of the I components is 0. Omega 1 I cross omega 2 L2 cosine of theta j gives us omega 1 omega 2 L2 cosine of theta k. Omega 1 I cross omega 1 L2 sine of theta k gives us negative omega 1 squared L2 sine of theta j. The omega 2k cross omega 2 L2 sine of theta I gives us negative omega squared sine of theta j. And then crossing that term with omega 2 L2 cosine of theta j gives us the omega 2 L2 sine of omega 2 squared L2 cosine of theta I. And then combining both of these parts, we'll notice that one of the k terms cancels out. The omega 1 omega 2 L2 cosine of theta k is negative here and positive here, and the rest we just combine them and rearrange for the final answer.